Hello and welcome back. In this video, I'm going to introduce a very important concept that we're going to use throughout the rest of the year, and this concept is vectors. So exactly what is a vector? Well, the standard textbook definition of a vector is an object which has both magnitude and direction. So exactly why do we need a vector? Well, if we consider, for example, what happens to the position of an object that's thrown off of a building, we can see that if an object's thrown horizontally, maybe I'll get a path that looks like this. If I throw an object vertically upwards, maybe I'll get a path that looks a little bit something like this. So just looking at these two examples, we can immediately see that the path that an object takes depends on the speed that the object is thrown, which is its magnitude, and it also depends on the direction that the object is being thrown. We denote a vector by placing an arrow above the variable. So for example, here we've got the change in position, velocity, acceleration, and force. All of these things are vectors, and the arrow above them indicates that these things have direction. When we talk about vectors, we call normal numbers like 2 or 3 or 4, something that doesn't have direction. We call those things scalars. There are two ways that we can write a vector. One way is we can list the components, and this is called component form. So for example, if I want to talk about the change in an object's position, I could say that an object is 4 meters east and 3 meters south from where it started. Alternatively, I could just explicitly state what the magnitude and direction of the vector are. So for example, I could say that an object is 5 meters from where it started in a direction that's 37 degrees south of east from where it started. A component of a vector is the amount of a vector that points along a specific direction. So for example, in the previous slide, 4 meters east is the component of the vector that's in the east direction, and 3 meters south is the component along the south direction. When we list a vector in component form, we simply state the two components of a vector. So for example, we could say the x and y components or the north and east components. Another way that we can write a vector in component form is we can put the x component and then a comma in the y component. When we do this, we place the vector between angular brackets, or the components, between angular brackets. The reason we use angular brackets instead of parentheses is to emphasize that this is a vector and not a coordinate. The reason this is important is because the laws of physics are the same everywhere in the universe. So for example, if I drop a ball off of the roof of, say, Western Albemarle and it falls to the ground, it's going to fall to the ground in exactly the same way as if I drop the ball off of any other building. So we don't need to refer to absolute positions. It's sufficient to just talk about the change in an object's position, or the relative motion. So just an example of the component vector. If a person walked, say, for example, 10 meters in the x direction and then 2 meters in the negative y direction, we could express her displacement as 10 meters, comma, minus 2 meters in between these angular brackets. Now, two vectors will be equal if and only if both of the components of the vectors are equal. So if I say vector A is equal to vector B, this means that the x component of vector A is equal to the x component of vector B, and the y component of vector A is equal to the y component of vector B. We visualize a vector by drawing an arrow. To kind of give you an example of how this works, let's just consider an example. So if A is minus 1, comma 2, the way we would represent this vector is we would draw an arrow starting at some arbitrary point, and we go in the x direction minus 1 from here, and then we go in the y direction plus 2, let's say this is 1, 2, and then we just draw an arrow from that initial point to that final point. And that's vector A. Now remember that vectors don't depend on absolute position. So any vector which goes over 1 and up 2 represents vector A. So all of these arrows here are vector A. Now at the beginning of this video, I said that a vector was something that has magnitude and direction. And up to now we've been talking about components of vectors. So how do we calculate the magnitude of a vector? Well, the magnitude of a vector is given by this formula here. So the magnitude of vector is the square root of the x component squared plus the y component squared. From this definition, we can immediately get some insight into the graphical representation of vectors. So if I have a vector A, which has an x component A sub x, and a y component A sub y, so I could represent this like, here we've got A sub x, here we've got a y component A sub y, so I can represent the vector with this arrow here. The length of this arrow is going to be equal to the magnitude of the vector, because we can see here that this arrow is at the hypotenuse of a right triangle. And we know that the hypotenuse of a right triangle is equal to the square root of the sum of the squares of the two sides. So we can see that the length of this is going to be the square root of ax squared plus ay squared, which is the same thing as this formula that we get for the magnitude of a vector. So let's look at a simple example. This example says, suppose a girl walks 4 meters east and then 3 meters south. What will be the magnitude of her displacement? So here we've got a displacement vector. If we wanted to write this in component form, it's going to be 4 meters east, and then it's going to be 3 meters south. So if I say north is the positive direction, then the component along the north-south direction is -3 if north is positive. Now, the magnitude of this vector is just the x component squared, so that's this first component, so we have 4 meters squared plus the second component squared, so -3 meters squared, and then we square root this. So here we have 16 square meters plus 9 square meters squared, and the sum of that is 25 square meters squared, which is just 5 meters. So that's how we calculate the magnitude of a direction. So now how do we calculate the direction of a vector? Well, if we're lucky, a vector might point along a coordinate. So for example, if the vector points in the x direction or the east direction, all we have to say is that it's 5 meters east, or so many meters per second vertically upwards. But most of the time a vector isn't going to point along the coordinate direction. It's probably going to be somewhere in between. So how do we handle something like that, where the vector is not pointing along the coordinate direction? Well, in that case, we describe the direction using an angle. So for example, I could say a vector is 30 degrees north of east, or 55 degrees clockwise from the x direction. It's very important that any time we discuss the direction of a vector using an angle, we have to say how the angle is being measured. So here it's 30 degrees north of east, 55 degrees clockwise from the x direction. If all I said was 55 degrees, that doesn't mean anything. You don't know how I'm measuring the angle 55 degrees. Now just one thing to be clear, north of east, what this means, this is a very common notation. So if this direction is north and this is east, north of east means I'm starting in the east direction and I rotate towards the north direction. So that's this angle here. So this would be 30 degrees. So let's look at a simple example. So this is the same one we had before. So a girl walks 4 meters east and 3 meters south. What's the direction of her displacement? So when we talk about the direction of a vector, it's very useful to just draw a picture of what's going on. So we want to just use a graphical representation of the vector. So here we have 4 meters east and 3 meters south. So let's go ahead and draw that. So if this is north and this is east, we went 4 meters east and then 3 meters south. So this arrow here represents the displacement. Okay? So using this, I can calculate, say for example, this angle right here. So looking at this picture here, we can see that the tangent of theta, right, that is opposite over adjacent, is going to be equal to 3 meters divided by 4 meters. So if I want to calculate this angle here, we see that theta is the arctangent of 3 meters divided by 4 meters, or 36.9 degrees. Now again, remember, I can't just say 36.9 degrees. It's 36.9 degrees with respect to what, right? How am I measuring this angle? So looking over here, if this is east, and this direction here is south, this angle is south of east. And that's a very common way to denote south of east, or north. You just put the first direction and then an O in the other direction. So let's consider just another example. What if instead of walking, what was it before, first east and then south, what if she walked, say, 3 meters west and then 4 meters north? Well, again, let's just draw a picture of what happened, okay? So we're talking about 3 meters west, right, and then 4 meters north. Okay? So this angle right here, we already know that. That's going to be 36.9 degrees. But what is that? Well, if this angle is theta, this angle up here is also theta, and we can see that this angle is going to be what? If this is north here, right? This direction over here is west. So this angle right here is west of north. So we see that the angle is equal to 36.9 degrees west of north. So again, now let's just look at another example. What if she walks 4 meters south and 3 meters west? So we're going to go 4 meters south, and then, I should have put that on the other side, and then 3 meters west. Not a very good triangle, but that's fine. So again, this angle right here, it's the same angle, right? There's still 4 and 3, right? I still have the arctan of 3 over 4. So we know that theta is going to still equal 36.9 degrees. But now this thing right here, if we think about this, this is north, this is east, this is west, this is south. So this angle here is west of south. So this is how we find the magnitude and direction of a vector if you know the components of the vector. But what if I give you the magnitude and the direction of the vector and you need to figure out the components? Well, this is what we call decomposing a vector. So decomposing a vector, that means you're going to find the components of a vector given the magnitude and direction. And the way we do this is we just use trigonometric functions. So let's look at a simple example. So the first example says a vector A has a magnitude of 10 meters and a direction of 30 degrees north of east. So just like before, the easiest way to start this is by drawing a picture. So if I say this is north and this is east, so here we have a vector that's 10 meters and a direction that's 30 degrees north of east. So here is the east-west component of my vector, right? So if this is A sub, say, E, and this is going to be A sub, say, N for the north. So if I denote my vector with the east-west component first, and then the north-south component second, we can see that the east-west component, this is adjacent to the angle 30 degrees, right? And of course the magnitude here, this was 10 meters. So this is adjacent to the angle. So we can see that cosine of 30 degrees, remember that's equal to adjacent over hypotenuse. This is AE over 10 meters. So I can solve for A sub E by multiplying both sides by 10 meters. So if I multiply by 10 meters, it will cancel the 10 meters. If we multiply by 10 meters over here, I see that A sub E is 10 meters times cosine of 30 degrees. Now if I want to find the north-south component, the north component is opposite the angle of theta. So I'm just going to erase this to give myself some room. So remember, opposite over hypotenuse, that's sine of theta. So we have sine of 30 degrees is equal to a sub n divided by 10 meters. So we see that a sub n is 10 meters times sine of 30 degrees. So now if I just plug all this into a calculator, I can see that the vector is 8.66 meters east and 5 meters north. Oh, and I gave myself some room there to work. Let's go ahead and just look at one last example of decomposing a vector. So this example says, let's consider a vector B that has a magnitude of 13 meters and is in a direction that's 22.6 degrees east of south. So what's going to be the components in this north and east directions? Okay, so once again, we want to just draw a picture. So if I call this north and this east, this vector points, let's see, 22 degrees east of south. Okay, so it's going to be something like this, right? It's east of south. This is going to be south. Actually, let me go ahead and extend this down. So this is the south component of the vector B. This is the east component of the vector B. This is the vector B right here. Okay, so, and this angle right here, this is our 22.6 degrees, right? We said east of south. So here is south towards the east direction, so that's what this angle is here. So once again, we're just going to use trigonometric functions to find the northeast, southwest components of this, okay? So again, going with the same convention I did before, we'll have the east-west first, so we'll have B sub E, and then we'll have the north-south second, so B sub N. And I'm going to assume that the east direction is going to be positive and the north direction is going to be positive. Okay, so the east component, now look, this is going to be opposite the angle theta, okay, because it's opposite, remember, opposite over hypotenuse, that's sine. So here we'll see that the east component is going to be this 13 meters times sine, 13 meters, times sine of 22.6 degrees. The north component, well, we can see that the vector actually points south, okay? So south, that's like the negative of north, okay? So the south component, the north component of this will be minus 13 meters times cosine of 22.6 degrees. Right, it's cosine because this is adjacent to the angle theta. So if I plug this into a calculator, I see that this is 5 meters east and minus 12 meters north, or 5 meters east and 12 meters south. So this is how we decompose a vector. So in the next video, I'll talk a little bit more about how we use mathematics, or how we add vectors, how we subtract vectors, how we multiply vectors, just how we perform basic mathematical operations with vectors.